All right, this is going to be our homework solution video for section 2.4, continuity. So on this video, I will work out some of the problems from the homework, not all of them, just a few to get you started in case you have any questions. So the first problem I'm going to work out is number 6. Problem 6 says, sketch the graph of a function that's continuous except for the stated discontinuity. So number 6, where they want us to draw a graph, so we'll put our axes down. And then it says it has to be discontinuous at -1. So here's 1, here's 2, here's 3, here's 4, here's 5. Here's -1, -2, -3, -4, -5. So they want it to be discontinuous at -1 and 4. Okay, so I'm going to put a D right here, discontinuous and discontinuous. That tells me when I draw my graph, I have to have a discontinuity at those 2 points. But continuous from the left at -1 and from the right at 4. Continuous from the left. So we have to use our definition of continuity, our one-sided definition. Now, that would say then that the limit as x approaches -1, that's what we're working with here, from the left of f of x has to equal f of -1. That's our left-hand definition of continuity. Now, it doesn't matter what y value we assign. So I'll just pick this number right here, and I'm going to put a solid dot. That's going to be f of -1. That's my y value for -1. Now, my function has to be continuous from the left, which means my function comes in, it has to meet that solid dot. If that was an open circle, that would still be not continuous, because if that was an open circle, then we would not be equaling f of -1. So now we're continuous from the left at -1. It also says we have to be continuous from the right at 4. So again, we can make our y value anything we want. We'll put this y value down here. It has to be continuous from the right. So as we come in from the right, we need a function. Make sure we draw a function. So now we have a graph that's continuous from the left at -1, continuous from the right at 4. That definition would look like this. The limit as x approaches 4 from the right of f of x has to equal f of 4. So we have right-hand continuity here, left-hand continuity here. Now, it says in the instructions, our graph has to be continuous everywhere else except those 2 points. So to keep it a function, right, we need an open circle here. Now, again, the y value you pick is completely arbitrary. I just happen to pick that one. We'll put an open circle here. Now we still have a function because for every x, there's one and only one y. And then we just need a function that's continuous between those two. And now we have a function that's continuous from the left. It's discontinuous on the right because our limit is going to this value, right? From the right, our limit is going here. But our functional value is there. So our limit is going to a negative number, but our functional value is a positive number. That's a discontinuity. Same thing happening over here. Our functional value is negative. Our limit from the left, right? From the left, our limiting value is up here. That's not equal to f of 4. All right, so that's an example. And again, those values that we've used for y, those are completely arbitrary. All right, so that's how you do problem 6. Problem 7 is similar to that. So let me erase this. And then we'll take a look at problem 9. Okay. Problem 9 is a word problem. And, you know, for some of us, we're just getting started. We're not really accustomed to looking at a word problem and thinking positively about it before we start. So let's see what it says. It says a parking lot charges $3 for the first hour or part of an hour. and $2 for each succeeding hour, or park up to a daily maximum of $10. Sketch a graph of the cost of parking at this lot as a function of the time parked there. Okay, so this is problem number 9. So we know as soon as we drive into the lot, right? As soon as we, like, for example, if we don't come in the lot, it's going to cost us, now this is our dollars and this is our time. So if we don't come in the lot, it's not going to cost us anything. But as soon as we drive into the lot, it's going to cost us $3 until we're there for an hour. So here's 1 hour, and that's going to cost us $3. So we'll put an open circle here and we'll come across like this. So for any part of the first hour, it's going to cost us $3. Remember, this circle's open right here. All right, it's an open circle. Now it then says $2 for each succeeding hour, or any part of the next succeeding hour. So if we park for another hour up until 2 hours, it's going to cost us another $2. So now we've spent $3. We're going to spend another $2. So now we are responsible for a charge of $5. Because as soon as we stay here for a minute after an hour, we owe them another $2. Then if we stay here until we're at 3 hours, we owe them another $2. So now we're up at $7. So now we have an open circle here, and we come across until 3 hours, and now we owe them $7. If we park for 3 hours, we owe them $3 for the first hour, $2 for the next hour, and $2 for the next hour. 3 plus 2 plus 2, that's $7. Now, what happens if we stay a 4th hour? Well, if we stay a 4th hour, we owe them another $2. So now we're up to $9. But what happens after that? Well, it says in the problem, the most they're going to charge us is $10, right? That's the most they're going to charge us for a day. After the 4th hour, we can park there as long as we want. The maximum we're going to pay is $10. So from here at $10, we have an open circle, and this just goes to the right forever because it's never going to be more than $10. That's the most we're ever going to owe them. So that's part A. Part B says, discuss the discontinuities of this function and their significance to someone who parks in the lot. Well, we're continuous from the left, continuous from the left, continuous from the left, continuous from the left. And then here we're continuous all the way across. We're not continuous at this point. So what is the significance to the people that park in the lot? Well, every hour there's going to be a jump discontinuity, right? Every hour there's a jump. So as soon as we hit the hour mark, it costs us another $2. So that's problem number 9. So let's see what's going on with problem number 11. All right, what's going on there? Problem 11 gives us some information. It says f of 3 equals 5. Okay. And it says the limit as x approaches 3, the limit as x approaches 3 of 2 times f of x minus g of x equals 4. I don't know why I'm writing a 5, it equals 4. All right. Now, what do we know? By our rules of limits, right? By our rules of limits, we know this is 2 times the limit as x approaches 3 of f of x minus the limit as x approaches 3 of g of x, and we know that equals 4. Okay, that's just using our limit laws. The limit of a function minus a function, we can subtract the limits. A constant times a function, we can put the constant out front. That's our limit laws. But we're given other information. We know f and g are continuous. Now, what does that mean? If f is continuous, that means the limit as x approaches any number, say 3, for example, since that's one they gave us over here, of f of x equals f of 3, right? That's the definition of continuity. That's literally the definition. So we can take this limit right here, and we can put the 2 down, and we can replace that limit with f of 3 minus. But g is also continuous, right? G is also continuous. So the limit as x approaches 3 of g of x equals g of 3. So we can do a similar substitution over here, and we can replace this with g of 3. Now we know what f of 3 is, right? We were given f of 3 as 5. So this becomes 2 times 5 minus g of 3 equals 4, or 10 minus g of 3 equals 4. And so g of 3 equals 6. So to do that problem, we had to use our limit laws and our definition of continuity. They're just reinforcing for us the definition of continuity over and over and over and over and over again, making sure that we remember that definition. Okay. Now the next problems assigned are 16 and 17. So it says, explain why the function is discontinuous at the given number a, sketch the graph of the function. So let's take a look at 17. Okay, we'll take a look at 17. 17 gives us a function, and it's a piecewise defined function. It says f of x equals, we have 3 pieces here. We have cosine of x if x is less than 0. We have 0 if x equals 0. And we have 1 minus x squared. That's a parabola that opens down if x is greater than 0. And it says, explain why the function is discontinuous at the given number a. Here, our a, right? Our a is 0. Now, then it says, sketch the graph. Well, we're in a calculus class. The graph is the key. We should draw the graph first. So let's draw a graph of what this function looks like. At 0, it equals 0, right? So at 0, we have a dotted 0. So here we go. We've got that. There we go. If we're bigger than 0, we're the parabola that opens down, right? Negative x squared parabola that opens down. It's moved up 1, right? It's moved up 1. 1 minus this. So because just real quick, f of x equals minus x squared. That's just your friend, the basic parabola that opens down. And then when you add 1, it shifts the graph up 1. So we're going to get this graph shifted up 1. I'm going to put this as an open circle because it's strictly greater than. And my graph is going to go down like this. Okay, so we have a jump right there. Again, the discontinuities become more obvious if we draw the graph first. On the other side, we get the graph of cosine, right? Now, what do we know about the graph of cosine? Well, the graph of cosine starts here and goes up and down, right? That's how cosine goes. So on this side, cosine, right? Cosine looks like this. This is our graph of cosine. So this is our function, right? This is the graph they've asked us. to draw. And they want us to tell them, explain why this function is discontinuous at 0. It's discontinuous at 0. Now, when we do an explanation, we don't want to say because there's a jump. That's not an explanation. Yes, that's a jump discontinuity. But when they ask us to explain, they want us to invoke the definition of continuity and show that it's not met. So for our function, the limit as x approaches 0 of f of x, right? Newton's idea of putting the bead on a string. If we put the bead on the string and get closer to 0 from the right-hand side, if we put the bead on the string and get closer to 0 from the left-hand side, this limit equals 1. But, right? It says explain. So they're expecting us to write a sentence. But f of 0 equals 0, which is not equal to 1. Therefore, f is discontinuous at x equals 0. This is all we're expected to do, right? We draw the graph and we write a brief explanation. We don't have to make this into a 4-paragraph essay. All right, so that's problem 17. Now, when we get to problems 19 through 24, of which they asked us to do 23 and 22, it says explain using theorems 4, 5, 7, and 9 why the function is continuous at every number in its domain. State the domain. All right, in class, on a quiz or something, I don't expect you to remember theorems 4, 5, 7, and 9 by their number. We're going to know what the theorems say, but we're not going to remember them as theorem 4 or theorem 5 or theorem 7 or theorem 9. So if we take a look at problem 22, all right, let's take a look at problem 22. The function we're given here is g of t equals the natural log of t squared, t to the 4th minus 1. Now, if all we had to do here was just explain why t to the 4th minus 1 was continuous for all numbers in its domain, we could say, well, that's a polynomial. It is, right? This is a poly. So we could say, well, that's a polynomial. Polynomials are continuous everywhere because their domain is all the reals. And we would write that out in a quick sentence and we would be finished. But again, when they say explain, they expect words, punctuation, capitalization, right? That's what we expect. So what do we have? We don't have just a polynomial. We have a composition of two functions, right? We have a composition of two functions. And lucky for us, we have a theorem, right? We have a theorem that says if f is continuous at b, and the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x equals f of b, right? That's theorem 8. Now, when you read that theorem, it really kind of confuses you, right? And so if we take a look at theorem 9 says if g is continuous at a and f is continuous at g of a, then the composite function, that's what we have here, is also continuous at a. So what is that saying? Well, here's what it's saying to us, okay? It's saying if you have a function, right? If you have a function, and we're going to call this function g, and we're going to call this function f, and this is the composition of two functions. The theorem says if the inside function is continuous at a number, okay? If the inside function is continuous at a number, and then the outside function is continuous at all of the outputs of the inside function, and I'll draw you a picture here just in a second, then the composition is continuous. So we have to go inside and see. So let's take a look at what we're talking about here. Here's our function g of x, right? What does g of x look like? Well, g of x has a domain and g of x has a range. Now, what is g of x? G of x is t to the fourth minus 1, and that's a poly. Right? That's a polynomial. So what does that mean? Well, that means the domain is all the real numbers. Any number we can plug in, and we're going to get a real number out. Now, what's the range of t to the fourth minus 1? Well, if we put a 0 in here, we get negative 1. Right? That's true. If we put 0 in here, we get 0 to the fourth minus 1. That's negative 1. If we put another number in there, right? A different number, like 6. Well, now we're going to get 6 to the fourth minus 1. That's a positive number. If we put 2 in there, we get 2 to the fourth. That's 16 minus 1. That's a positive number. What does the graph of t to the fourth minus 1 look like? This is where knowing our functions and their graphs really comes in handy. T to the fourth is a graph that goes like this. It looks similar to a parabola, but it goes up faster. It's not a parabola. We don't call it a parabola. Parabolas are squares. When we subtract 1, we move the graph down 1. So t to the fourth minus 1 looks like this. Now, the domain of that is all the reals. But we're asking ourselves, what's the range, right? What are the outputs here? What are the outputs? Well, the outputs are everybody from negative 1, right? This is negative 1 right here, negative 1, all the way to infinity, right? So the range g of x is greater than or equal to negative 1. That's our range, right? So our range is the set of y's such that y is greater than or equal to negative 1. But we have a second theorem, sorry, a second function here. We have our outside function, the natural log. We have that function on the outside. So our f of x, that's the natural log of x. And we have to have a similar conversation about what's its domain and what's its range, right? What's its domain, what's its range? Well, the natural log of x, the graph of the natural log of x looks like this. You can only plug in numbers greater than 0. The domain here is the set of x's such that x is greater than 0. Well, why is that important? Because the way a composition works, right? The outputs of this inside function become the inputs of the outside function. We go in first, out second, right? That's our order of operations, work on what's inside. So if you ask me to evaluate this, right? If you ask me to evaluate this, and I'm going to plug in, let's say I'm going to plug in 3. Let's do 2. We're going to plug in 2. I put 2 here, it gives me 16 minus 1. I get the natural log of 15. That's how it works. It goes here first. This spits out, when I put in a 2, it spits out a 15. 15 becomes the input into here. Well, the problem we have is the natural log can't handle 0. Well, if we take a look at our function over here, it equals 0 right there and right there. Those are bad. The natural log can't take those. So what happens if I plug a 1 in here? 1 to the fourth is 1 minus 1, that's 0. Now I try to plug a 0 into the natural log. 0 is undefined. That's a vertical asymptote. The natural log can't handle 0. So I have to make sure my output here is never going to be 0. Now, how do I do that? Well, I eliminate those 2 numbers. This one's 1, and this one over here is negative 1. Well, what happens if we plug in a 0? Right? What happens if we plug in 0? 0 to the fourth is 0, minus 1, negative 1. The natural log you can't take the natural log of negative 1. Negative 1's here, it's not in the domain. So this is a bad number. In fact, all of these numbers right here are bad. Right? These are all bad. So the domain of this function is the set of x's such that x is less than negative 1, right? These over here are good, they work. Or x is greater than positive 1. And now our theorem 9 says this function is going to be continuous. It's going to be continuous because the polynomial is continuous everywhere. And we know that the natural log, because it's a log function, is continuous on its domain. That's one of our theorems. So we found the domain, and now we know we're continuous on that domain. Okay, that's a lot. I understand. You can watch this video, you can back that up, watch it 3 or 4 times. We need to understand how this continuity and composition relationship goes together. So that's 22. What about 25? Let's take a look at that. '25 says locate the discontinuities of the function and illustrate by graphic. Again, drawing the graph in the beginning, often way easier than trying to draw the graph at the end in a calculus class. We should always think about starting with the graph. Right, so this is our function. Right, this is our function. So we have to ask ourselves, what does a graph of this look like? Right? What does a graph of this look like? Because if we draw the graph, we're going to be able to see the discontinuities on the graph. So let's start with, whenever you're trying to find, the domain of a function, you always start with 0, right? That's what we always did in Algebra 1. Can we plug in 0? Well, if we plug in 0, 1 divided by 0 is undefined. So 0 is not in the domain, right? 0 is not in the domain. So I'm going to draw an asymptote right here on my graph, because 1 divided by 0 is undefined, therefore 0 is not in the domain. Now, is there anybody else not in the domain? Are there any other numbers that I have to eliminate? What happens if I put a 1 in here? I get 1 divided by 1. That's 1. E to the first is E. Right? E, remember, E is 2.781828182845, and it goes on and on and on forever. Right? It's just a number. It's 2.781. So that would be 1 plus 2.78. Well, that's a number. And 1 divided by that, it's going to be around 1/3. So if we plug in a 1, we're going to get a number out. It's going to be close to 1/3. Almost close, I guess it's closer to 1/4, because that's 2.7 plus 1, 3.7. It's closer to 1/4. What happens if we plug in a 6 or a 12 or a 10? Well, if we plug in a 10, I get e to the 1/10. Right? That's the 10th root of e. Well, the 10th root of e is smaller than e. When I take the 10th root, right? Because 1 over 10, that's the 10th root. So I get the 10th root of e. Because that's e to the 1/10. Right? That's what they taught us in Algebra 2. Now, what do we know about this? Well, we know this is less than e, right? Smaller than e. So I've got 1 plus a number smaller than e. So before it's about 1/4, right? But now I'm smaller than a 4 on the bottom. My denominator is actually getting bigger, right? My denominator is getting bigger. If I put 100 in here, I get e to the 1/100th. That's the 100th root of e. And that's small, right? That's tiny. If I put 1,000 or 10,000 in there, I get e to the 1/10,000th. That's the 10,000th root of e, and that's really tiny. So as x gets bigger and bigger and bigger, right? That's what we're asking ourselves if this is x. As x grows, This goes to 0. And I get 1 divided by 1. This has a horizontal asymptote at 1. What does it look like when I plug in a very tiny number? I mean an infinitely tiny number. Well, if I plug in a tiny number, right? We plugged in 10, we plugged in 10, then we plugged in 100. This isn't obviously the scale. We plugged in 1,000, and our graph is getting closer and closer and closer to 1. What happens when we plug in a tiny number? Well, what's e to the 1 over 1 over 10? Well, that's e to the 10th. Right? That's what that is. E to the 10th is huge. That's 2.718 dot 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 to the 10th. That's 3 to the 10th. That's big. Now I've got 1 plus a big number. That's a big number. 1 divided by a big number is 0. So as I plug in a tiny number here, we're getting closer and closer and closer to 0. But positive or negative? Positive or negative? Well, we're never going to be negative. There's nothing here that's going to be negative. So this graph, right, this graph comes down like this and gets closer and closer and closer to 0. Now, it can't get to 0. 0 is not the domain. What about negative numbers? What if we put a negative one there? Well, what does that look like? What if we put a negative 1 there? We get e to the 1 over negative 1, which is e to the negative 1, which is 1 over e. So this becomes, right, this turns into 1 plus 1 plus 1 over e. Well, 1 over e is about 1/3. 1 plus 1/3 is 4/3. 4/3 in the denominator is 3/4. So if we plug a negative 1 in here, we're at 3/4. We're positive. But what happens if we put negative 10,000 in there? By the way, welcome to calculus. This is what we do, right? We play these games and we ask ourselves, what if? And of course, it would look like this, right? So if I put negative 10,000 in there, what is that going to look like? Well, that's e to the negative 1/10,000. Well, that's 1 over e to the 10,000th. That's what negative exponents do. E to the 10,000th is huge, right? So this turns out to be 1 over a huge number. That's 0. So this piece turns out to be 0. So we get 1 over 1 plus 0. We get 1. So on this side, it's doing the same thing. It has a horizontal asymptote at 1. Now, the problem says, locate the discontinuities of the function, illustrate by graphing. Well, we have a discontinuity at 0. F of 0 fails to exist. The definition of continuity says the limit as x approaches a of f of x has to equal f of a. And our 3-part definition, part A says f of a must exist. Well, it doesn't. It does exist everywhere else, though. So it's continuous everywhere else. All right, so that's problem 25. I understand. There's a lot of number crunching going on. There's a lot of mental math. Yes, that's what this turns into. We have to be able to, and if we can't do this kind of math over here in our heads, then we have to write it down like I did and think about it, or grab our calculator, see what, what's the trend? What is the behavior of the function? What is it doing as I put different values in? That way I can draw the graph. (31), 33, those are very similar. 35 says, for what value of the constant c is this function continuous? All right, so let's take a look at that one. 35. It says f of x, it's a piecewise defined function. And we have cx squared plus 2x if x is less than 2. And then we have x cubed minus cx if x is greater than or equal to 2. So when we draw our graph, over here at 2, right? At 2, what do we know about our function? Well, we know that's a polynomial. That's equal to 2. So when I plug in 2, I'm going to get a number. I don't know if it's positive or negative. I don't care. I'm going to get a number. So I'm just sketching it over here. So I'm going to get a number there. That's a polynomial. It's also valid when x is greater than 2. So it's a polynomial, so it's defined everywhere. What about if x is less than 2? Well, that's a polynomial. So it's defined for everybody less than 2. Now, our big worry is, what happens if it does this? Well, then it's not continuous. But the problem says, find the value of the constant, so the function is continuous. In other words, they're saying, find me a value of c, so that when you take the graph the other side, it comes in and it intersects, right? This is less than 2. This is greater than or equal to 2. So by them telling us we want it to be continuous, that means no jump, right? No jump. So we got to draw it so it runs. So those two things have to be equal when x is 2. We need equality when x equals 2. That way our two sides of our graph touch each other. So what are we going to do? Well, we're going to plug in 2 and make them equal to each other. If I plug in 2 here, I get 2x squared plus 2x. I need that to be equal to, what do I get when I plug? Wow, that is 100% wrong. X is 2, right? So I need it to be x is 2. So I'm going to put an x there, a 2 there, pardon me. So that's c times 4, so that's 4c plus 2 times 2, that's 4, equals x is 2, that's going to be 8, minus x is 2, that's 2c. So I bring the 2c over here, that gives me 6c. I bring the 4 over here, that gives me 4. So these are going to be equal when c is equal to 4 divided by 6, or 2/3. The key is, and again, you can go back and watch the problem again for the build-up. The key is we need them to be equal when x equals 2, so we don't have a jump. So that's problem 35. What about 41 and 44, right? 41 and 44. Let's take a look at those. Those involve the intermediate values there. Okay. (41) and 44. So 41 says, use the intermediate values theorem to show there's a root of the given equation in the given interval. So 41, we have x to the fourth plus x minus 3 equals 0. And we know this interval is 1 to 2. So the first thing we have to do is we have to say f of x equals x to the fourth plus x minus 3 is a poly. Thus, f is continuous on 1 to 2 because it is continuous on all reals. See, we can't use the intermediate value theorem if we haven't first established continuity. We gotta have continuity. So we've established that. And now what do we need? We need the intermediate value theorem. We're trying to show there's a root. A root, remember a root occurs. Here's 1, here's 2. This function would have a root between 1 and 2 if the graph crosses the x-axis. Now, I don't know which way it crosses. It could go increasing like that, which this function is, but it could be decreasing and have a root over here, right? I don't know which way the function goes. I mean, we know this function's increasing because it's a polynomial and x to the fourth is positive, so therefore that function's going up to the right. We learned that in pre-calc. But the key is we've got to show it's negative someplace, positive someplace else. If I can show it's negative here and positive over here, and I don't have to plug in 1 and 2. I can plug in any number I want in this interval. But if I can show it changes from negative to positive and it's continuous, the only way the graph can go from below the x-axis to above the x-axis and be continuous, i.e. I can draw without lifting my pencil. I have to touch the x-axis. And if I touch the x-axis, it has a root. It doesn't ask me to find the root. It says show a root exists. So we'll check f of 1. F of 1 is 1 to the fourth plus 1 minus 3. That's going to equal 2 minus 3. That's negative 1, which is less than 0, i.e. it's below the x-axis. Then we're going to check f of 2, right? F of 2 is 2 to the fourth plus 2 minus 3. 2 to the fourth is 16, plus 2 is 18. Minus 3 is 15, which is greater than 0, i.e. it's above the x-axis. And so we could say, therefore, by the intermediate value theorem, f assumes all values between f of 1, which equals negative 1, and f of 2, which is equal to 15. So f must equal 0 between 1 and 2. Therefore, f has a root in our interval. Look, we're in a college class. We're expected to write things, not just jot things down. Okay? We're expected to express our thoughts clearly, concisely. All right, that's the expectation. All right, so that's how we do 41. 45 says it's a calculator problem. It's got a cosine, and it wants you to find an interval that contains a root. And so the functions are cosine x and x cubed, right? And what do we know? We know the graph of cosine. Here, I'll give you a hint how to get started. We know the graph of cosine goes like this. And we know x cubed goes like this. And they want you to find a solution, right, of cosine x equals x cubed, or they want you to find a root of cosine x minus x cubed equals 0, right? We can move that over there and then talk about roots because it equals 0. They want you to find this point right here. How are we going to do that? Well, we're going to use our calculator and we're going to try to find an interval of length 0.1 that contains a root. So they want us, we know this is cosine, right? So we know this is 2 pi. We know this is pi. We know this is pi over 2. And so somewhere between 0 and pi over 2, there's a place where these two things are equal. And we can start looking for that spot, right? We can start looking for that spot. Just plugging numbers into our calculator. 49, we don't have to worry about 49. All right, so that's my video on section 2.4. I hope that helps. Everybody have good luck with your homework.